Hello, I'm Aleksey Veresov, and I'm going to present my thesis abstracting frameworks away from stateful dataflow systems done under the supervision of Professor Philipp and Jonas Spenger. So let me start with an overview of the presentation. First, I will go through the introduction. Then I will introduce the model describing stateful dataflow systems, which are actually the first small step operational semantics of asynchronous barrier snapshotting, which is the key algorithm used in stateful dataflow systems. Then I will go through the introduced definitions of the thesis, mainly a novel definition for failure transparency, which is a property capturing correctness of failure handling. And finally, I will go through the proof of failure transparency of the model. And in the thesis itself, I also present the proof technique in more details. And after that, I will conclude the presentation. Also, I have to note that one of the contributions of the thesis is that the model, the definitions, and the theorems are mechanized in Coq, which is a proof assistant. Okay, so here's some related work, and now I can start with the actual presentation. So the thesis is about failures, particularly failures in distributed systems, and they are notoriously hard to handle. So just as a few examples, Google's apps crashed for around an hour in 2012. 20. Facebook services were down for 6 hours in 2021. And Cloudflare had an outage for around 6 hours in 2020 due to a Byzantine failure, which is quite a wild beast. Essentially, it means any kind of failure. It can be malicious misbehavior or anything at all. In this thesis, I focus on crash failures, which are failures in which computers just do not respond to anything. They don't do anything. Also, they don't do anything bad. They don't misbehave maliciously. They just don't do anything. Okay, so, and formal methods are the preferred solution for handling failures in distributed systems. Mainly because testing doesn't work that well, and formal methods are able to eliminate all the cases in which test coverage is not really practically achievable. So, for example, Amazon and Microsoft applies them to AWS and Azure, and other companies also show interest in them. However, again, the topic of this presentation is not failures in distributed systems in general, but a more specialized type of failures in stateful dataflow systems. And stateful dataflow systems are a class of distributed systems, the most prominent examples of which are Apache Flink, Google Dataflow, Azure Event Hubs, and multiple immersion systems, including portals on which Jonas is doing his PhD. And stateful dataflow systems essentially describe distributed programs as directed acyclic graphs of processors, which are essentially stateful functions processing some messages which they send to one another, and maybe affecting local persistent storage in some way. So the key feature of stateful dataflow systems seems to be that there is no need to handle failures manually in them. They are handled automatically. And I would say that this is the reason for their widespread use. So, for example, in Uber and ByteDance, they report that they use Flink to serve more than billions of events per second. However, although this property is very useful and very important for stateful dataflow systems, there is no general formal definitions applicable to small step operational semantics of this exact property, namely failure transparency. That is, no previous work is applicable to any of the mentioned systems, although they claim that they provide this property. So the goal of this thesis is to formulate this and proof for a model of these systems. Okay, so how do they handle failures automatically? They do it via what is called, in most general form, rollback recovery. That is, if we have a program and it behaves for a while and we observe a failure of one of the processors in the system, then what we can do is we can collect a certain consistent state from the local persistent storages of processors of this program. And then we can just use this checkpoint to restore to it and continue a normal operation. Particularly in stateful dataflow systems, the algorithm which they use is known as asynchronous barrier snapshotting, in which sequences of messages on the input streams of processors are delimited by barriers, which are by barriers into groups named epochs. And the algorithm itself consists of 4 steps, local for each processor. So first of all, on each processor, we process each of the input streams up to the barrier, and then we stop and don't consume from this input stream anymore. And we do so until all barriers on all input streams are aligned on the processor locally. In this case, the processor propagates the barrier and saves its current state to the local persistent storage. And after that, we just continue a normal operation for the next epoch. Now, as I mentioned, the way to handle failures is formal methods. And particularly in this thesis, I use small step operational semantics. And here I'm going to shortly introduce it. So in small step operational semantics, the meaning of programs and the meaning of programs is described using derivation rules, which look like this. They contain promises on top, which are logical formula which have to be satisfied in order to derive a conclusion which is below the line. So in this case, this rule says that if we have a function add with 2 arguments and the arguments are integers, then the result of application of this function is C, which is sum of these 2 integers. However, if we want to execute a nested program with nested add functions, this rule alone is not enough, and we have to introduce 2 rules which propagate the execution to the left and the right arguments of the function. But in this case, it is possible to execute the same expression in several ways. So in this concrete example, we can first apply the left rule, then the right rule, and the main sum rule, or we can first apply the right rule, the left, and then the main rule. This property may seem confusing or something like this, but actually it's very useful to capture asynchronicity of distributed systems, particularly the message passing, because this non-determinism enables to very efficiently and concisely capture what we don't know also. Okay, now I can go and introduce the stateful dataflow model, which I devised. So it is a small step operational semantics of asynchronous barrier snapshotting based systems, consisting of essentially 5 rules, in total 7. And only 3 of these rules describe the whole failure-free part of the system. So 3 rules are enough to describe normal operation of these ABS-based systems. Then 2 more rules are related to failures, particularly failure introduction and recovery from them. And another 2 rules are auxiliary. They are needed for just handling the symbols correctly. Okay, so the main rule is called S step. It looks like this. And here in the premises, we see a local step on a particular processor P from one state to its updated state, which produces some actions, X, that is message production or consumptions. And then these actions are applied. And if we can derive such a local step on a single processor, then we can derive via this rule a global step for the whole program. So that's its meaning. Now, what are the local steps? Well, the first of them is I-event for handling normal messages. It looks like this, but essentially it just says that we consume a message from any output stream, from any input stream, we don't know from which one, and pass it to the stateful function representing the actual program put inside this processor. And it outputs an updated state, and a set may be empty of output messages. So then we output the messages and also update the state. Okay, the second type of local rule, and the last one, is iBorder for handling barriers or borders. And in it, there are actually no premises, but certain symbols are bound in the conclusion, so these premises are just kind of hidden in the conclusion. So here it's stated that they should consume borders from all input streams, and it works this way that we consume from all streams because we mention n in both cases, in the definition of a processor and in the action for consumption of these borders. And then, if we have this border alignment case, we can output the border, propagate the epoch border, and we can update the state, save it to the archive with A in the next state of a processor, and we increase the epoch number of a processor, so we switch to the next epoch. So that's all. That's the whole failure-free part of the stateful dataflow model. But as I mentioned, we also have failure-related rules, and they are fortunately quite simple. So failure rule says that if we have a processor, it can fail. That's all. There are no premises, nothing. It just can fail at any moment, and in this case, no other rule will be applicable to it. And for failure recovery, it's a global step, so it's a step on the whole program, on the whole directed acyclic graph, which says that if we have a failed processor, we can restore the whole program to its latest common snapshot. That is, we take a certain implicit coordinate that calculates the latest common epoch number and sends a command to each processor to restore their state after processing this latest common epoch. This is what this latest common snapshot means. It also removes all in-flight messages. Okay, now we can continue to the third section and define failure transparency. So just to build an intuition about what it means to be failure transparent, I would like to show an example of it. So let's suppose we have an execution of our program. Executions are just a sequence of configurations which are derivable according to the semantical rules of the system. So let's suppose we start with this state, then we receive a normal message with 1 in it. Then we process aligned borders, and then we process another event 3, and then we fail, and recover and continue the normal operation from the checkpoint to which we have recovered. So in order to claim that the system is failure transparent, for each such faulty execution, there should be an execution without failures, such that we can we can map all observations of our real system to this idealized failure-free model. In other words, faulty executions should not produce anything unobservable in not faulty executions. And to capture this formally, I introduce two auxiliary definitions. First of them is observational explanation, which is a property which relates to executions, C and C prime, according to the observability functions O and O prime. They're just functions which take the state of the program at any given moment and return some kind of summary of it. Particularly, they return an object or the state which is observable by the user of the system. And intuitively, the property means that all observations reachable in original can be reached in the explanation. So it captures exactly the relation which I showed on the previous slide. And to note here is that we actually map all of them for prefixes, and you may think that maybe it is possible to explain, for example, in this case, C4 with C2 or something like this. In other words, that it is possible to explain something from the future with something to the past relative to already made mappings. But it turns out that this definition actually doesn't allow this kind of situation to occur. So essentially, it also captures the meaning of history in the sense that time cannot be reversed. You cannot go back in time. The next definition is observational explainability, which is more or less the same property, just lifted to the level of systems, that is sets of small step operational semantics derivation rules. And in this case, intuitively, it means that for each execution of a translation, its source should observationally explain it. In other words, no matter how exactly we execute something in our faulty model, it still should be explainable by the idealized high-level model, failure-free model. Okay, now we're ready to capture failure transparency, and it is simply observational explainability of a system by its failure-free part. That's all. In symbols, it looks like this. So we have the same system, and we remove failure-related rules from it. And then we say that we just take the same state, the same set of initial states, and we use the same observational function. And yeah, in this case, we should be able to observationally explain the real model by the failure-free part of it. Intuitively, this definition means that for each valid program, no execution with failures produces an observation which cannot be achieved in its execution without failures. Yeah. And the nice thing about this definition is that it is quite general, and it is possible to apply it to a wide range of models, particularly any small step operational semantics with explicit failure-related rules. And another nice property of these definitions is what I call composability of observational explainability. That is, in the previous slide, we have defined that failure transparency is a property of this type of form, right? So we have a high level, we have a low level, and the low level is observationally explained by the high level. But what if we want to go even deeper? What if we want to go even closer to the real software, which we potentially want to verify and prove some properties about it, not about this intermediate model which just introduced failures? In this case, because of this composability of observational explainability, we can just prove the same property just with different observational functions for these two systems, which is easier to do than to do the big arrow from the very top to the very bottom. And then if we find some kind of lens function O double prime, which transforms O tilde to O to the same observational function as in the theorem which is proven in this thesis, we can automatically derive the big theorem going from the very high level to the very low level. And yeah, as I mentioned, the idea here is that this proves that these results can be reused later to actually verify the real software. Okay, now the last section, the proofs of failure transparency of stateful dataflow. Here I will explain only the general idea of it. And the most important idea here is to introduce causality or causal order or happens before relation, and to exploit some nice properties of it. So it is defined in this way. There are three cases when something happens before something else. First of all, A happens before B if it happens before it on some processor. Second case is if A was sent to P prime, and then after it was received, P prime produced B. In this case, A also happens before B. And the last case is just transitive closure of it. So if there is a C such that A happens before C and C happens before B, then A happens before B. Okay, but why this definition is useful? Because there is causal consistency. That is, for example, if we consider this kind of split of our execution, we can notice that the sending of M to 2 is not included in our split, but its receival is included in our split. And this is a problem because M to 2, the production of it happens before its consumption. So this type of split of history is not okay for us. It's not causal consistent, so it's causally inconsistent. But if we draw it like this, if we include the production of M to 2 but not its receival, then it's perfectly fine. And it is useful because we can reorder our history as long as we don't break causal relations. So the results which are produced at any moment by these two systems are the same. They cannot be different because we don't break causal consistency. Okay, now finally, the general idea of the proof of failure transparency for stateful dataflow systems. It's a constructive proof in which we go from a faulty execution with some failures and recoveries to an observational explanation of this original execution. And we do this in 3 steps. First of all, we split the original execution into generations by the recovery steps. And then inside each generation, we reorder things, preserving the causality relations. And then we just strip the prefix of all the events which are discarded in the recovery. And because causal consistency guarantees us that everything is fine, even if we do this, we can just join these reordered and stripped generations into the failure-free observational explanation. So that's it. Conclusion. As a summary of this presentation and thesis, failure transparency is defined so that it's widely applicable. The definition of failure transparency enables easier proofs via history manipulation compared to inductive approaches. The first operational semantics of asynchronous barrier snapshotting is provided. Asynchronous barrier snapshotting is proven to provide failure transparency now. And That's it pretty much. Now I also want to mention possible future work. So I thought that it would be interesting to mechanize the proofs presented in the thesis. It would be also nice to provide even lower and higher level models of stateful data flow systems using this composability of observational explainability. And finally, I think it's also interesting to explore end-to-end failure transparency of heterogeneous systems which use different algorithms to handle failures. Thank you.